All right, the next one was it a center of mass or was it a centroid? Center of mass. Okay, so let's write down those equations so we remember what they are. Mass is equal to, was this a double integral or a triple integral problem? Triple integral. Okay, so mass is going to equal to integral over the shape t times the density function lambda of x, y, and z, dy, dz. Okay? And the center of mass will be found with either x, y, or z. We'll just look at x here because they're all the same. So this is the x coordinate of the center of mass. X sub m is equal to the integral t x times lambda. Okay. So really what that tells us is that the x coordinate of the center of mass is going to be equal to an integral divided by an integral. And don't forget that. Okay. Because remember, the center of mass is, the equation of the center of mass is xm times m is equal to this stuff, but m is defined up here. So in order to find, this should have an x right here. No, this should have an x. Sorry. Okay. So remember, if it's centroid, what changes? Remember what changes if you're doing centroid instead of center of mass?
X bar.
I mean, pretty much. Lambda equals 1. Okay, if it's homogeneous, then you have a constant. But if it's centroid, you're just basically finding... Centroid's like the somebody help me, geographical center, right? Geological has to do with rocks. So geographical center, the center of mass has to do with which part can you put your finger on and balance it. You put your finger anywhere. What part can you put your finger and balance it? Okay, so... For that, we have x bar, that's called a centroid, and it would be times the volume is equal to triple integral over t, x, dx, dy, dz. And remember, the volume is just equal to the triple integral over t. Dx, dy, dz. Okay. So remember, if you ask for the centroid, it still should be a division of two integrals. We're not asking you to evaluate these integrals. So if you have a test tomorrow, what's the center mass, what's the centroid? You should have a big integral, some triple integral, divided by some triple integral. Okay? Cool.
So like this, sorry, the centroid would be like that divided by the volume.
This divided by this.
Okay.
Yeah. So you would just take the v over and put it on the other side. All right? So let's do this, let's work out this problem, because all this problem is are just practicing limits of integration and how to set up the integral. Which has all to do with pictures. You know, can you visualize it? You know what's going on. This one's hard to visualize. Okay, so this one says, you have the line z equals, or the plane z equals 0, the plane z equals 2 minus x. You got two planes, and then you have x squared plus y squared equals 2x, which is a cylinder, right? And this is a cylinder. If you complete the square, this is the cylinder, x minus 1 squared plus y squared equals 1. That's not as important. But this helps you see where it is. All right? But right off the bat, this one tells you you have to use polar coordinates. Right? So it says using polar coordinates, do this. Okay? So we already know we have to do a switch to polar. So everywhere we see a z, we change it to a z, right? Z doesn't change in cylindrical coordinates. So everywhere we see an x, we change it to r cosine theta, and everywhere we see a y, we change it to r sine theta. So right here, this tells us x squared plus y squared, that's r squared, equals 2x r cosine theta. Okay. And z is going to go from 0 to 2 minus r cosine theta. Right? And from this equation, we get that r is equal to 2. Okay? This is kind of all the information we got without really drawing a picture, right? Oh, is it 2 plus x? I just, sorry. I didn't look at it. Okay? So we know what z is going to and from. We have an equation for r. Well, maybe we should draw this picture and see what's actually happening in r. What we have in the xy plane, looking at this, I can draw the picture really easily. I got a circle shifted over like this. That's really small. I'm sorry. I'll draw it bigger. Okay, and this is the cylinder. Goes up and down. Okay, and we already know what it's capped by in z, so I'm not worried about that. We know that it's capped by this equation. So you can draw it out. There's going to be some plane, 2 plus x, so x equals minus 2, and z equals 2. So you have this line going like this, and then it slices it, and whatever. Okay, we got our plane, and then we drag our plane across the board this way in y. So we get our line going in and out of the board, and then we drag it this way. But since we've already had the smooth switch to polar, we don't care. We just got to figure out what r and theta is doing now. Okay, this is my equation for r. So we know that it's r equals 2 cosine theta is this circle, right? We got that from this right here. We know that this cylinder is this equation, right? So we know that it's all the r's are going to be inside this circle, so it's going to be underneath that. We have to think, okay, so where does r start? R starts at 0. R is bigger than 0, so r is positive, and it's maximized by this thing. Okay. Okay, so if r is positive and maximized by this thing, what's theta doing? Well, you can think of it two ways. What values of theta makes r positive? Negative pi halves to pi halves. Or you can think about it, remember the first and fourth quadrant are positive cosine values? Yeah. Or, I don't like to think of it that way. I like to think of it this way as what values of theta gets me one rotation for r to start at 0 and get back to 0. Because we know r starts at 0 and gets back to 0, and r equals 2 cosine theta gives me this circle as theta goes. So theta goes from something to something, and it gives me this circle. Well, we know it starts at 0 and ends at 0. So where does cosine start at 0, and where does cosine end at 0? Yep, negative pi halves to pi halves. And when it gets to 0, we're going to be at r equals cosine of 0, which is r 2 times cosine of 0. So r equals 2 times 1, r is 2. R is 2 is going to be right here. So theta equal to 0 points me this direction. R is 2 points me to this point right here. Okay. So we know that theta is going from negative pi over 2 to pi over 2. What sweeps this circle exactly one time? Okay. So then now we have boundaries. Now we know our volume. So our volume is going to be equal to negative pi halves, 0 to 2 cosine theta and z equals 0, and z equals 2 plus r cosine theta. Okay, remember our Jacobian. Z r d theta. That's our volume. Okay, and we know that we want the center of mass in z direction, right? Do you have a question or are you just stretching it out? That's fine. So, Cm is going to be this exact same thing with the z plugged in right here over top of this volume. Site, it said it was homogeneous, so lambda function is a constant. So we have some constant. Right? I shouldn't just blow that off like it's nothing. Remember the equation I wrote up here where lambda, x, y, and z was the density function? We said that the density is homogeneous. Now, density homogeneous means that density is constant throughout, but it doesn't necessarily have to be 1. Okay, so it could be 7. It doesn't change the... If you forgot this on a test, you wouldn't get any points off. Okay, if you forgot to put a k here. But this just, whatever k is, that's the density of this weird shape getting cut by this plane. Okay, it's a cylinder with a plane going through it. Alright, so you got to throw the k in there. Okay, so if we want to know Zm, we would have to do, from the equation, it was this exact same thing right here. Now I'm just going to call this t so I don't have to write it all again, but the endpoints are the exact same. So I'm just going to call it t. Zrk dz dr d theta divided by the volume. Okay? And remember, you don't have to evaluate the integrals, you just got to set them up. So once we get here, we're done. Alright, we know that v is this, and Zm is